Any other questions? Okay, let's go now to the Blac-Scholes equation. Blac-Scholes equation. Now, how did we get the Blac-Scholes equation? Remember that if I write S here, and I have S here, then this is going to be squared here. So this is the ethos lemma we're going to use for the Blac-Scholes. Now, Blac-Scholes. What it says is we start off with a portfolio, which is equal to V of S T minus alpha S. And the question is to try to find what is the change of that portfolio. Now, is that the only portfolio you can use? No. Why this one? I'll tell you in a minute. But what we have is, according to the Blac-Scholes equation, or ethos lemma, excuse me, the rate of change of the portfolio is going to be the partial of V with respect to S minus alpha, partial of V with respect to S minus alpha, delta S plus the partial of V with respect to T, delta T, plus 1/2 sigma squared S squared, the second partial of V with respect to S delta T. That's going to be the first part of your derivation. Okay, everybody with me on that? Okay, a couple of you are still writing down quickly, so I'll pause for a second. Seconds up, okay? What we have then is the only risk, or the main risk in here is the delta S equals mu S delta T plus sigma S delta X. And this is the risk. That's the risk, the S delta X. The delta X term is randomness. And so what we do is to eliminate the risk, what we do is get rid of that term. In doing so, we get rid of a lot of terms. So I'm going to get rid of this term right here by setting alpha equal to the partial of V with respect to S. And remember, V can be PS T, or V could be CEST. V could be just about anything. Now, and here's a key factor. We're really interested in finding the value of the call or of the put. We're not really interested in finding the value of this particular portfolio. So, what does this equation give me? To use an analogy, let's suppose we got a game between the Lakers and the Heat. No. That's not a game. That's not even a warm-up. Okay, let's say, who? Cleveland. And? Cleveland and the Lakers? No, Heat. Heat. All right, Cleveland and the Heat. Who are you going to take?
Heat.
Heat? Yeah. What odds are you going to give? 4-3. What odds? You're going to take Cleveland. What odds are you going to give?
2-4.
2 to, come on, give me other odds. Bigger odds. Say 2-1.
Yeah, sure.
2-1. Okay. He says 2 to 1. He says 4 to 3. You now know from the first week how to find what is the right odds to have to balance these two hedges. Suppose he changes it to 3 to 1. Your answer is going to change. Your answer will change. You know that just from the algebra. Similarly, right here, this alpha right here, this partial of V with respect to S, what that does is it gives you the balance between the value of the call and the value of the asset. In other words, what we're doing is in the hedging equation, the purpose of the hedging equation is to find the value of the call put, whatever option you're looking at, relative to the current price of the asset, the current action of the asset. Okay? And as I said, this is equal to delta. Alpha is called delta. And so really what this is it says here is the call, here is the price of the asset, and this right here gives you the ratio of change, between the current price of an asset and what's going on with the asset, and the current price of the call and what's going on with the call. So it gives you the action between his bet and his bet. His bet, okay? And so that's what it does. Okay? Everybody with me on that? So therefore, parts of the Blac-Scholes equation is to give us information concerning how does the price of a call vary relative to, action and the current price of the asset. So what we have now is that delta let's see if this one right here works. We have that delta V, delta portfolio rather, equals, by setting alpha equal to this right here, and at each time interval, you take a look at your how partial of V with respect to S is coming, and you adjust your portfolio that amount so that you have this balance. This term crops out, so all we have left is the partial of V with respect to T, delta T, plus 1/2 sigma squared S squared, the second partial of V with respect to S, all times delta T. That's what we have so far. That tells you how the portfolio is changing, how the value of a call is changing relative to the current price of the asset, the current action of what's going on. Okay? Because the partial of V with respect to S, that depends on how fast S is changing and how fast V is changing relative to S. So it's giving us all of that information just like we had in the beginning of the course. The next step is to find what is the change in this value of this asset. Call, this option, relative to what's going on elsewhere in the market. See, so far I'm just doing it with respect to this particular commodity, this particular asset, and the call or put. But I have to take into account what else is going on in the world. And the way we do this is we look at a bank. And we have delta bank profit is equal to R V minus S times the partial of V with respect to S, delta T. So it is taking this amount of money out, going short on this, taking that amount of money out, putting it in the bank. The interest rate is R, so it's R times the amount of money times delta T, which is what we've had before. What does this do? This tells you how it is adjusting, how it is Yes.
Should that be V minus alpha S?
V minus, yeah, but alpha is equal to the partial of V with respect to S. That's what I'm doing. Okay. He says, shouldn't I have V minus alpha S? And what I've done is substitute in the value of alpha. Thank you. I've substituted the value of alpha in there. Okay? Any questions? Okay. And now what happens is how can we put these two together? Why should these two be the same? Well, our good friend, arbitrage. Arbitrage. You can use it in two different ways. One way you can use arbitrage is that if I get more money in the bank, I'm getting rid of, I'm going short on this. If I'm going short on this, the price is going to adjust. If I get less money from the bank, I'm going to go long on that. And I'm going to adjust. And so the prices are going to go in the right way. Or in the bank, you got your bank, you didn't realize it, but she owns a bank. I know you're so rich. Okay. And what she wants to do is attract customers. If a lot of people are depositing, the interest rate is what attracts them. She's going to lower the interest rate. If a lot of people are not, she's going to raise the interest rate to attract them. But notice, this interest rate does not depend on that commodity alone. It depends on the market. What happens in all of the different commodities. And so this is by arguing that we can go long or short on this, is where we can put them together. And I get that this is by curvilinear equal sign. We get this is here. And I then am able to connect the value of the option with what's going on in the market. Because the market is going to affect the interest rate. Okay, any questions? All right. And if I set them equal, they both have a delta t, I can cancel, and I have the Black-Scholes equation, the partial of v with respect to t, plus 1/2 sigma squared s squared, second partial of v with respect to s, plus rs, partial of v with respect to s, minus rv equals 0. That's the famous Black-Scholes equation. And why is it of such value? I just told you. It captures the value of the option relative to what's going on with the asset and the option. That's the partial of v with respect to s. That's the delta term. And what's going on with the market. That's the R term. The market as reflected by the bank. So this is the reason why the Black-Scholes equation plays such an important role in the finance world. Now, there's another reason. The other reason is not everybody, but a large enough people believe in it. And so if a large enough people believe in it, they make their markets accordingly. And if a large enough people adjust according to the market, well, that's what's going to happen. The market will behave in that fashion. But here is the equation. That's the Black-Scholes equation. If you want to find the value for a call, you change V for CE. If you want to find it for a put, you change V with PE. Yeah.
Well, I I have a doubt. When I build my portfolio, I don't know, buying or shorting a number of shares such that alpha is equal to the derivative of my option to S. But that's the derivative I have now. I don't know, imagine my strike price is very, very under very under the current price or vice versa. But I'm not sure, sometimes I saw options whose rate of change of the price of the option was changing depending
All
on
right.
the underlying
Okay,
the
what do
price
you-
of the underlying.
He's asking an important question. He's saying, with this portfolio, how in the world do you compute this, right? How do you compute this is one of the questions he's asking. Secondly, he's saying, whoa, suppose my strike price is lower or larger or something else. How do I? Well, a lot of the questions he's asking, which are excellent questions. What happens if the strike price or the time to expiration or any of these others? What happens is I change them, which is part of what this question was. And the answer is, we'll find out when we get the solution to this partial differential equation. A lot of your questions will be answered. Second, he's asking the following question. How in the world, because if I'm managing my portfolio, I know that if I'm going to try to find what is the value of my option relative to the value here, and if I have going short and long in this fashion, he's saying, how do I know what alpha is? How do you compute the partial of V with respect to alpha? S rather. Any answers? How about you?
I'm not sure.
He's not sure. How about you? You? Nope. But you're from Switzerland. They got all kinds of money there. Okay. So what happens is, how do you find an approximation for f prime of x? So how do you find the value of f prime, approximation for f prime of x?
Taylor series.
Taylor series is one, absolutely. You could do that because if for Taylor series, you could have that the change in f is equal to f prime of x times the change in t plus higher order terms. Divide through here, and I have an approximation for f prime. How is f of x plus h minus f of x divided by h is an approximation for f prime of x. Correct? And so therefore I would expect that the partial of v with respect to s from market data is v plus h minus comma t minus v of s comma t over delta over h. So market information can give me an approximation for what's going to be alpha, called delta. Okay. Good question. Okay, so that's what we have there. Any other questions? Yeah.
Has alpha to be a constant?
No.
No. Could be a function.
It's yeah. Here's where there's a little song and dance. We have to have it a constant, but it's not a constant. And so what are we doing here? We're doing a little adjustments here. We're doing a little hand waving here.
Rounded.
Yeah, you got it. And so really what happens is that how do we use it? In fact, is at the beginning of each time interval, maybe in the morning. You check to see what is going, you compute what alpha has to be, and you make adjustments accordingly, and you hold it a constant for that period. And that's really what the way in which it's used. But what happens is that alpha is a constant, as we have right here. Otherwise, I'd have to take the partial of this with respect to s if I didn't, and t. So we treat it as this way right here. So we treat it as a parameter which is constantly being adjusted, is what we do. Excellent question. Any others? All righty. So that's the Blac-Scholes. Now what we have to do is we just have the, wait a minute, something seems wrong here. I have one equation for the put and then the same equation for the call. How can that be? Wouldn't I get the same answer? We know they don't work the same way. What do I need? How can I distinguish between them? Let's see. And to give you an idea, what we have is x double dot is equal to minus g, as you know from the first course in physics. So that equation handles both this. That equation right here handles both this. And it handles that. Okay. What was the difference? The initial conditions. That what we need is we need initial conditions. That the difference is the differences are initial conditions. You throw in different initial conditions, you get different kinds of solutions from the same law of physics or finance. Okay? What we need now is we need to find out what are the kinds of initial conditions. And in fact, they are called boundary conditions. And to handle these, I'm going to write down an equation which is not the Black-Scholes equation, but what is very close to the Black-Scholes equation. And we'll find out how close it is a little later today. Yeah, today. And that is very transparent. That is the equation for heat flow. Let's see if this one works. I'll take this one along with me. Let's see, for heat equation. The heat equation is, it's got some parameters, we're going to forget them. The heat equation is the partial of U, this is the heat at any point xt, with respect to T, is equal to the second partial of U with respect to X. That's the heat equation. And what is that? Here I have a bar, and it is 20 units high. And I want to find out, I got bringing the bar from outside. Not that bar. Bringing the bar from outside. And then I do something to it. I want to find out how the heat changes as time goes on. Okay? And so let's use common sense what we need to know. So here I have X goes between 0 and 20, and here is the time interval. Well, if you think about it for common sense, what do I need to know what's going to happen to that bar?
What the temperature?
I need to know what the current temperature is. And so I need to know what is the current temperature of the bar. I need to know that function right there. So that's the boundary condition. I need to know what's the temperature of the bar along at time 0. When we bring it in from outside, I need to know what the temperature is at each point. And suppose that function, just pretend, suppose that is equal to 100 over 20, x. So in other words, that here it's 0, here it's equal to 100 degrees. I don't know. Whatever your problem is, that's what you have. But that's the initial conditions of the bar when you bring it in. What's going to happen next depends on what you're going to do to that bar. I could put a blowtorch on both ends. I could put a blowtorch on one end and an ice cube on the other end. Or I could put an ice cube on both ends. You're going to get different solutions, aren't you? Common sense tells you you're going to get different solutions. So this means that I also need to know what am I doing to this bar for all time? What am I doing to this bar for all time? Am I putting a blowtorch on it? Am I putting, if I put it on ice on top there, that'll be equal to 0 for all time. And so it goes across. Okay? Then I also have to know what am I doing to the other end. What am I doing to the other end? And so common sense says that if I have the bar and I know what it is when I bring it in from outside, and I know what I'm doing to this end and I know what I'm doing to that end, I can be able to tell you later on, the equation will tell me what's going on in the bar as that time moves on at different locations. And a bit later, should time permit, I'll show you how to numerically put it on Excel, a spreadsheet or something, how to get answers for these type of questions. Okay, any questions? All right. The next question is, fine, big deal. How do we use this for calls and puts? Well, we have a little difference here. Notice this equation here. This is the partial of u with respect to t equals the second partial of u with respect to x. This is the partial of v with respect to t equals minus the second partial of v with respect to s. So they're going in different directions. The heat equation is going forward in time. Blac-Scholes goes backwards in time, which is fortunate. Which is fortunate because I don't know what is going to happen at any other time. I only know what's going to happen at expiration date. So let's write down what the equations are going to be. And let's do this for the call. So if I can find what are going to be the boundary conditions, then I can find what's going to be the solution. You know the solution, you go out and you become rich. Remember this course. All right. So what we have is I have to find something which corresponds to ux0. In other words, what happens at time 0? Well, we don't want it at time 0. I want to find the conditions CES at time t. That's what I want to find here. That takes the role of finding out what the bar is at when I bring it in from outside. Now I'm trying to find out what's going to happen at expiration date, and I'm going to go backwards in time to find out what's going on today. So what is CE? Want to put that away? What is CE ST, S capital T? What's that equal to? S? Is it just S or what? Okay. So we've been looking at this all along. We know what this is equal to. At expiration date, we know this is equal to the maximum of S minus E, 0. It's equal to the maximum of S minus E, 0. Very good. So therefore, here is E. It's going to equal 0 here, and then it's going to start moving up. Okay, everybody with me on that? Okay, now I want to find what is U20T. That's going to be, what's the upper bound? What's the upper value for S? How large can S get? Infinity, yeah. S can get arbitrarily large. So, we got a little trouble here, because this is going off to infinity. And I got to find what is the value over here. Well, suppose E is 100, and suppose S is 1,000,000. What do you think is the difference between S and E? It's essentially 1,000,000. Basically 1,000,000. And the larger and larger S gets, the closer and closer it gets to just a value of S. Forget that E, it's so darn small. And so therefore what we have is the upper boundary is CES for any value of T as S gets very large is essentially, let's do it this way, CSET is essentially equal to S for S large. So that will be the upper boundary. It's so, you know, if I get up to it, you got a call. Are you fortunate? He got a call. E for $100, and now he looks at the market and it's worth $20 million. It's the jackpot. Okay, no, what's it up to now? The jackpot. 40 million, I think it's up to. It's up to $40 million. And so what happens is, what he did, you know, he bought a ticket for 40 minutes. It was the right one, Powerball. And so what's the difference between what he paid and what he gets? Forget what he paid. It's worth that large amount. And so it says that the call is essentially worth S. And now all we have to do is find the lower bound, because we got the upper boundary, this boundary, we just got to get the lower boundary, C, 0T. If S is equal to 0, what do you think is going to be the worth of the call? If the price is 0, what do you think the worth of the call is going to be? 0. Now you got to prove that. And so I'll just give you an outline. It's in the notes. I'll give you an outline why it's true. But this is 0. The trouble here is that perhaps miraculously, the value S is equal to 0, and perhaps miraculously, all of a sudden the market starts shooting off. Well, it can't. With this governing equation. Because if S is equal to 0, the change in S always is 0. So therefore, if S ever gets to 0, it's going to stay 0, according to our theory of how the prices change. So there are the boundary conditions for call. What I want you to do now is find the boundary conditions for a put. Go ahead. Find the boundary conditions for a put. Okay, let's get started. You know what it's going to be here. The value of a put is what? Maximum, correct, of E minus S0. Because at time t, difference between the put and the strike price gives you how much money you can make. What happens here? When you get close to infinity, when the price gets close to infinity, what's the put worth? 0, correct? Hard one. What happens on the bottom? That's the hard one.
Well, if the share goes to 0, I earn the whole E.
Keep going.
E? No.
Nope, not E. I don't get it until time t.
Yeah, no, I'm meaning in time. Okay.
But what about time a year before t? Well, let me show you. It's written in, I describe it in the notes. Maybe it's not in the notes you have, but the notes you will have by tomorrow. But the answer for all of these really comes from our friend, should be your friend by now, the put, call, parity. When in doubt, look at the put, call, parity equation. Hint, hint, hint. When in doubt, look at the put, call, parity equation. Because it gives you the value of the put, the call, the commodity, and the value of money, present value of money. Pardon?
It's the present value of the money.
That's right. So he says with this equation it becomes clear because we know that when s equals 0, we know that this is equal to 0. So this will be 0, this will be 0, so the value of a put is the present value of E dollars. The present value of E dollars. Actually, you can get all three boundary values directly from here. Because look, what happens is as s goes to infinity, these two things are starting to equal each other. This is minuscule, swallowed up by it, so that starts approaching zero. You get all of the boundary conditions from the put-call parity equation. And in fact, by Thursday, we will have the solution of the Blac-Scholes equation for the call. From the put-call parity equation, you have the solution for the put. You just plug and chug. Put it into the crank and turn that heavy crank around. Okay? Any questions? Anybody have a question that they don't know what to ask? Any liars? Okay. So what we have now, let's see where we are. Where we are now, it's that we started off by looking at what does the Blac-Scholes equation really tell us. The Blac-Scholes equation tells us how the value of an option changes relative to the action on the price of a stock, of an asset, how the activity relative to this. That's the partial of V with respect to S term. That's the alpha term. That by itself is not enough. We need to know how the value of the option is going to change relative to what else is going on in the world. The surrogate for what else is going on in the world is the bank rate. And so what we do is we set that equal to the bank rate as we did earlier, and we end up with the put-call parity equation. This part right here after we take a look and with the alpha equals the partial of V with respect to S, that part right there tells you how the market and the particular asset is changing relative to its option. And the rest of it says how does the action on this particular thing and the world connect in with the option. So we get all of that powerful, powerful information. Simple to derive, if you know Ito's lemma, but simple to derive. What was clever is putting this all together to say, how do we, that the price of an option has to vary relative to what's going on with that particular stock, that asset. And it has to go on with respect to the market, what's going on in the rest of the world. And so that's why we have this powerful equation. Any questions? The second part, what we did after we described where this came from, is we said we need more information to be able to find a solution. And the way we did this is we said, by using of the analogy of dropping erasers and throwing them all over the room, is that we have to have different initial conditions, different starting conditions. So therefore, we looked at what happens with a bar, and we found out what's going to happen to, what do we need to know how, what's going to be the temperature at the bar at this point right here in the future. Well, I need to know what was the initial temperature of the bar, distribution of temperature. I have to know what am I doing to the two ends of the bar. Here, I have to know for a call, I have to know what's going to happen at expiration date. I have to know what happens if the market collapses or if it gets incredibly strong. You put this down and mathematics says you can solve it. So that's what we've done so far. The next part, so that you have some intuition about what these terms mean in the solution, which you will get on Thursday. to find out what these terms mean when you get here on, when we talk about it on Thursday, is how do we solve that equation? How do we solve the Black-Scholes equation? What we're going to do is I'm going to show you how I take that ugly equation right there, the Black-Scholes equation right here, and we reduce it to this equation right here, the heat equation. By a lot of change of variables, we can change the Black-Scholes equation to the heat equation. And why is this of interest? Well, for several hundred years, we know the solution to the heat equation. We've known the solution for the heat equation since the 1700s. So therefore, once I get the solution for the heat equation, I take the solution, and I have the solution to the Black-Scholes equation. This is why, you know, I gave a lecture once at the physics department at the University of Chicago. And one of the faculty members said, you know, my son got his Ph.D. in physics and he's moving into finance. Why is he doing that? Well, one reason is you're going to get paid about twice as much. But the second reason is that a lot of the things, like Black-Scholes is related to the heat equation, you have a lot of intuition. A lot of the intuition you get from physics and from random effects, etc., carry over to the finance world. And so those were some of the reasons. And there's a lot of challenges in the finance world. We don't know what's going on. Okay. So the first problem we have is to get the S out of there. This right here has got S squared. That's the independent variable, S squared. This one doesn't have any. So what we want to do is I'm going to show you how to get change of variables to simplify the Black-Scholes equation. But we're going to start with the following. dy dx equals 3y. Now, this equation is pretty easy. What we know from what we did with money is that this can be written as 3 dy over y is equal to 3 dx, which means that the natural log of y is going to equal 3x plus a constant, which means y is going to equal e to the 3x plus a constant equals a constant prime e to the 3x. Now, there's a wonderful, wonderful thing that you had in your differential equations course, and you promptly looked at and said, does it have to be on the exam? You ignored it. It's called the uniqueness and existence theorems. And you probably asked, WAGAT, who cares? So let me tell you why the existence and uniqueness theorems for differential equation and partial differential equations are wonderful. It says that if you have a differential equation and you have this existence and uniqueness, it says there's going to exist a solution, and no matter how you find it, if you find a solution, that's okay. It's unique. So the uniqueness part of a differential equation theorem says, by guess, by gully, by trial, by error, whatever you do, if you get an answer, it is an answer. Don't worry about if it doesn't satisfy what you wanted to satisfy. If you got an answer, you're fine. Okay? So let's try the existence uniqueness with the following differential equation. So here I have a differential equation. Y double prime, see, I'm getting up to double primes, that's getting close to the second derivative. Y double prime minus 5y prime plus 4y equals 0. Maybe we have, to find what that constant is, maybe we have a condition such as y of 0 equals 1, y prime of 0 equals 4. I don't know, I'm just inventing them. How am I going to solve that problem? Well, the point is here is we don't, this problem, we know from theory that it has a unique solution and a solution exists. So no matter how I find that solution, it doesn't matter. So what am I going to do? I'm going to guess. I'm going to guess that the solution is of the form e to the mx. And what's m? I don't know. I got to figure out what m is. All right. So what do? Is we substitute it in. Y prime equals m e to the mx. Y double prime equals m squared e to the mx. And when I substitute in here, I have m squared minus 5m plus 4 e to the mx equals 0. All I'm trying to do is by existence theorem, uniqueness theorem, I know that if I can find an answer, it's going to be the answer. So I can divide by e to the x, and all I have to do is solve for this polynomial right here. And that means m is equal to looks like it's m minus 4, m minus 1. Am I right? Let's see. That'll give me 4. That'll give me minus 5. Yeah, equals 0. So therefore, m is equal to 4 and 1 are the solutions. So what did we do here is we just guessed the solution. We wrote down these properties. We found the value of m. And so now I know that the solution is going to be y of x is a constant e to the 4x plus another constant e to the x. Okay, any questions on what this is? I think some of you have already had this. How many have not seen this before type thing? How many haven't seen it before but don't want to raise your hand? Okay, good, then I can move. Okay, very good. So a couple of you shyly raise it, and so you see how to do this. So what we're doing here is we're just plain stating that uniqueness says there's going to be a solution, you just put it in. Alrighty, here's one that you most surely, or you probably did not see before. And that is x dy dx equals 3y. X dy dx equals 3y. How do I solve that problem? Any ideas?
Just move x to the right-hand side.
Move the x on the right-hand side?
Yeah.
Okay, if I do it on the right-hand side, then it gets even uglier. Then I have y over x.
Just by subcolumn, or you can solve that.
No, x is a variable. X is a variable, so that's a nice trick, but it won't quite work. So what do you do when you see something that's ugly? Remember what ugly is. Ugly is a change of variables. For you. So I'm going to try a change of variables to see what happens. What is that change of variables? I haven't got the slightest idea. So I'm going to have x dy du du dx equals 3y. And what is u? I don't know. I'm trying to figure it out. I have no idea what u is. I have no idea what to choose for u. But I see something that could make my life easier. If whatever I choose for u, wouldn't it be nice if whatever I chose for u that part right there happened to equal 1? If that part right there would happen to equal to 1, then I would have the equation dy du is equal to 3y. Oh, that looks familiar. And I would have u is equal to, y is equal to e to the 3u, is equal to a constant e to the 3u. Put it away. Would be equal to that. So I'd have the answer solved. There's only one problem. I don't know what u is. So how do I solve for u? Well, you've solved for u exactly the way I have right here. I want x du dx to equal 1. Du dx is equal to 1 over x. U is equal to the natural log of x. And so just by substituting and looking for good luck, I have y is a constant e to the 3 natural log of x, which is a constant x cubed. And there's my solution for this differential equation. Okay? So you see what happens there. Now let's go over the steps because you're going to have it for your homework tonight. What we have, it's that I know how to solve problems like this one right here, or this one right here. I don't know how to solve problems like this one right here, which is essentially the same thing as the Blac-Scholes equation, the problem with the Blac-Scholes equation, with that S there. So I got to figure how to get the S out of there. I got to figure how to get the X out of here. And what we do is we say it's ugly, so make a change of variables. X, dy, du, du, dx. This is just a chain rule. What would I like? I would like for this term right here to equal 1. X times this to equal 1. If this right here was equal to 1, I would then have the equation dy du is 3y. Same equation. Solve y equals a constant e to the 3u, and I then find what is u from here, substitute in, and I get the answer to the equation. Yeah?
So will a change of variable help us later? Because we can solve this one without one. So will it help us later?
No, we need this right here. We're going to need this to, you can solve it without it, yeah, but the trouble is you're going to need, because you put it over the, which is he said, put the dy and the 1 over x and solve it, you would have had the same thing.
Right.
But what happens is what you're going to do for second derivative now. And so the question that I'm going to ask you is, so we know how to solve this problem. What do we do here? Suppose I have this equation. Suppose I have x squared y double prime minus 4xy prime plus 4y equals 0. Now what are you going to do? Your approach isn't going to work now. So I want to solve this problem. If I could get the x's out of there, I'd be okay, wouldn't I? The trouble is, how am I going to get those x's out of there? How am I going to get those x's out of there? If there is justice in the world, I do like that one. Sounds like a defense attorney. If there's justice in the world, then the same change of variables should work. Then the same change of variables should work. So what is it that we have? I'm saying that if there is justice in the world, then the change of variables if there is justice, then this might work. In your homework, it's going to be a lot of problems of this type, so make sure you understand it. So what I have to do is I know this is going to be fine. So what I have is, let's do it, I don't want to get rid of this. So I'm going to have that dy dx is going to be du, dy du times du dx, which is equal to 1 over x dy du. Okay, so that will get rid of this x term right here. That's substitution. When I replace y prime with dy du, that'll get rid of the x. What I have to do is find the second derivative. So the second derivative of y with respect to x is the first derivative of the first derivative of y with respect to x, which is equal to d dx of 1 over x dy du So you see what I'm doing? I'm just writing down the second derivative because that's what I need right here. And I have to compute this. This is going to equal, it's a product rule, it'll be minus 1 over x squared dy du minus 1 over x squared dy du plus 1 over x, the derivative with respect to x of dy du Now I'm going to use the change of variable again. And so this is going to equal minus 1 over x squared dy du plus 1 over x du dy du times 1 over x, which is equal to 1 over x squared times minus dy du plus the second derivative of y with respect to u. Ugly. So that's what you get from the change of variables. And when I substitute into the equation, into this equation here, I'm going to have x squared times minus dy du plus the second derivative of y with respect to u minus 4x 1 over x dy du plus 4y equals 0. A lot of nice cancellations. The x squares cancel out, the x's cancel out. And what you end up with is the second derivative of y minus 5 dy du plus 4y equals 0. That this equation gets transferred into this equation. Yeah.
What happened to the 1 over x squared?
Okay. The 1 over x squared is right here. You didn't see it, did you? It was just too light on there. Thank you. Because the x squares have to cancel out then. That's the whole purpose. Okay? Any questions? All righty. So let me just review then what we've done. What we did just now is we now know how to solve some differential equations. Most of you have seen some of this. But how do we do it with variable coefficients? And here what you do is by luck and by a gully, what we can do is we find the change of variables and we get rid of the variable coefficients. That is precisely what's going to happen with the Blac-Scholes equation, which will be one of your homework problems. And this term right here is going to explain why we get certain answers in the Blac-Scholes equation. This product rule. I will try to get an extra session for tomorrow night. How many need an extra session? Well, I'll try to get an extra session for tomorrow night. Okay?